Good afternoon. Today we're going to talk about section 3.4, the product and quotient rule. So we already saw that the derivative of a sum of functions is the sum of the derivatives. That is, d dx of f of x plus g of x is equal to d dx of f of x plus d dx of g of x. But what about the product of two functions, d dx of f of x times g of x? What is the derivative then? And we actually have a rule for it, and we call it the product rule. So if f and g are differentiable at x, then d dx of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. Or, another way to say this is g of x times d dx of f of x plus f of x times d dx of g of x. And in this one, the order really doesn't matter, so you can do either or. F of x times d dx of g of x plus g of x times d dx of f of x, or g of x first. The order doesn't matter. What matters is that you have f prime of x times g of x element and an f of x times g prime of x element. And we can even expand this to 3, but that's neither here nor there. I'll show you in an example if it comes up. So let's do a quick example. So in this example, we're going to let f of x equal x cubed and let g of x equal x to the fourth. And from algebra, we know that x cubed times x to the fourth is equal to x to the seventh. So using just our regular power rule, d dx of x to the seventh is actually 7x to the sixth. So we hope that using the product rule, we can get something that looks like 7x to the power of 6. So let's d dx of x cubed times x to the fourth is equal to the derivative of the first, which is 3x squared times x to the fourth, plus the first, which is x cubed, times the derivative of the second, which is 4x cubed. So now we use algebra again, and we see that this is simply 3x to the sixth plus 4x to the sixth, and wham bam, thank you ma'am, we have 7x to the sixth. So whether or not you use an algebraic technique or you use a calculus technique, you're going to get the exact same answer. And granted, this was a pretty easy example. We're just using something that we can deduce algebraically. But the properties are still the same when things become irreducible. So if we have a product rule, we better have a quotient rule. And unfortunately, the quotient rule is not nearly as simple as the product rule. In fact, d dx of a function f of x divided by a function g of x is g of x times f prime of x minus f of x times g prime of x all over g of x squared. And there's a cute little rhyme I like to use to remember the quotient rule that I learned way back when I took Calculus 1 in 2012, which is low d high minus high d low all over low squared. So we call f of x is high and g of x is low. So we know that when we replace them, we're going to get the exact same thing that we want. So let's go ahead and see a similar example to the one we just saw. So this time, let f of x equal x to the fifth and let g of x equal x cubed. And from algebra, we know that x to the fifth minus, or divided by x cubed, is simply x squared. And d dx of x squared is simply 2x. So we hope that using the quotient rule, we get 2x out as a result. So d dx of x to the fifth over x cubed is equal to low, which is x cubed, times d dx of x to the fifth minus high, which is x to the fifth, times d low, which is d dx x cubed, all over low squared. So all over x cubed squared. Now I'm going to go ahead and simplify this step really quickly and just zoom through it because we know what the derivative of x to the fifth and we know what the derivative of x cubed is. So we have 5x to the fourth times x cubed, which is x to the seventh, minus 3x squared times x5, which is 3x to the seventh, all over x cubed squared, which is x to the sixth. So we can factor out 6 copies of x from the numerator and 6 copies from the denominator, and we're left with 5x minus 3x, which is simply equal to 2x. So we get the exact same answer whether or not we use the product or the quotient rule, or whether or not we use algebra to deduce something. So hopefully this proves to you that the quotient rule works just as intended. So let's revisit the power rule. And though it may seem redundant, the general form of the power rule is that if n is any real number, then d dx of x to the n is n times x to the power of n minus 1. And you might be thinking, well, what is this all about and why would I do this? Now we're not saying that this has to be positive. It can be negative. And that makes our life easier if we're trying to differentiate something like that. We can just turn it into d dx of x to the negative 3. And then we can apply our power rule, negative 3. Well, negative 3 minus 1 is negative 4. So we've got negative 3 over x to the 4. So that's just a quick example showing what exactly we mean when we say that this could be any real number. So here's a section I dubbed either or, and in some cases you can use either the product rule or the quotient rule depending on what is going on. So in this case, let's consider f of x equals 12x times e to the power of negative x. And I'm going to conjecture that I can use either the quotient rule or the product rule to find the solution to this. So let's get started. So here on this side, I'm going to use the product rule, which says that f prime of f should be, whoa, sorry, didn't mean to zoom in like that. F prime of x should be f of x, which is 12x, times d dx of e to the negative x, plus e to the negative x, times d dx 12x. So though it may seem not intuitive, we'll get to a reason in the next couple lectures why d dx of e to the negative x is negative e to the negative x. But we've got 12x times negative e to the negative x plus e to the negative x times 12. So fixing that all up, we've got 12 minus 12x all over e to the negative x. So we hope that using the quotient rule, we're going to get something pretty similar. And the quotient rule says that if I turn this into 12x over e to the negative x, then d dx of this beast should look like low e to the negative x times d high, which is 12, minus high, which is 12x, times d low, which is negative, d low, that should be a positive, my bad, which is just e to the x, all over e to the x times e to the x. And there's a reason I'm writing it like this, which will become clear momentarily. So this one should also be positive. I don't know what I'm doing there. So it should look a little something like this. And now we can factor an e to the x from the top and an e to the x from the bottom, and we get 12 minus 12x over e to the x times 1. So we do indeed get 12 minus 12x over e to the x. So in this case, you can use either the product rule or the quotient rule. And for me, the quotient rule is always pretty cumbersome to deal with, so if I can use the product rule instead, I usually do. So let's keep going with a few more examples. We can combine rules. So here you've got something and you can already tell that this is going to be like a pretty major situation, but we want to find the derivative of y equals quantity 4x squared plus 7 times quantity 3x plus 1, all divided by 8x minus 3. And I'm going to go ahead and use my product rule, or my quotient rule for this one, because it'll be pretty easy to set everything up. So dy dx is going to equal low, which is 8x minus 3, times d dx of high, which is 4x squared plus 7, times 3x plus 1, minus high, which is 4x squared plus 7, times 3x plus 1, d low, 8x minus 3. All of this over low squared, which is 8x minus 3 quantity squared. So from the product rule, d dx of 4x squared plus 7 times 3x plus 1 is equal to the derivative of the first, which is 8x times the second, plus the derivative of the second, which is just 3 times the first. So then you're going to plug and chug to get your final answer, which you can go ahead and check. I'm not going to show you all the algebraic steps to get here, but it's 192x cubed minus 76x squared minus 24x minus 119 all over 8x minus 3 quantity squared. Now, this sort of question might look familiar, and it looks familiar because I indeed took it off one of your homeworks, and I think what I'm going to do from now on is go through your homeworks and find questions that are maybe a little bit cumbersome and use those as examples, so that when watching the videos, you can have something directly in your notes to relate to what's going on your homeworks. So speaking of that, I'm also going to do a bonus question today. And this ties in with what we were doing in example 3.1, that supplemental video. But homework question 3.4. Find the equation of the tangent line for y equals 5x divided by x minus 3, where a equals 4. So the first thing we need to do, we've got y minus f of a equals m times x minus a. We've got a, we just need f of a, and we need m. So f of a is just going to be y evaluated at 4, which is simply 5 times 4 over 4 minus 3. 5 times 4 is 20 over 1. We're just left with 20. And now we need m. And m is going to be f prime of 4. So we need to find f prime. So d dx of 5x over x minus 3. We're going to do low, which is x minus 3, d high, which is 5, minus high, which is 5x, d low, which is the value 1, all over low squared, x minus 3 quantity squared. And then we're going to plug in so we get 5 times 4 minus 3 minus 5 times 4 all over 4 minus 3 quantity squared. That is equal to negative 3 over 1, which is negative 3. So m equals negative 3. Now we can plug on in. Y minus 20 equals negative 3 times x minus 4. Expand out. Y minus 20 equals negative 3x plus 12. Y equals negative 3x plus 32. And that's how you do that question on the homework. So that's going to be it for me today.